Yes, good day again, students. Welcome to my channel. Today's topic, we are talking about gravitational fields. And I have a small question there, so that our videos are short. The acceleration due to gravity on Earth is G, or it's 9.8. And then they go on to say, what is the acceleration due to gravity on a planet that is double the mass of the Earth and half the radius of the Earth? That is the question. And then there's a variety of choices there. I want to show us how we get to the answer. So the first thing that I'm going to ask is what the formula of acceleration due to gravity are we going to apply here? Okay, because we have the formula which says the weight of an object is equals to mg. So which means the acceleration due to gravity, you divide the weight by the mass of the object, but we don't have the weight of the object, is not even given. So what is given is the mass of the planet is doubled. So yes, which formula are we going to use here? We are going to use this one. G is equal to big G, big M over R squared, where big G is the universal gravitational constant, and big M is the mass of the planet, and R squared is the radius of the planet, right? So this is the formula that we can use. For example, when we're talking about the acceleration of gravity on Earth, it is 9.8. It is big G times the mass of the Earth over the radius squared. Good. So the approach that I use to answer this question is as follows. This is by G. Now we need what I call G nu, G subscript nu. So I'm writing here. So which means my G subscript nu is the acceleration due to gravity on the new planet. So it's going to be big G, the mass is double, so it's times 2 big M over the radius is half, so it's going to be half. Half of radius is R over 2, so that is R over 2. So it's R over 2, but that's all that is squared. Switch. So the next thing is, if you look at the choices of answers, they want us to know how many times bigger is the, or smaller is the G, the acceleration due to gravity on this other planet. So all we need to do now, let's finish this one. We find that G nu, there are two methods I was showing. G nu is equal to 2 big G, big M, all this over R squared over 4, which means I can, if you are dividing by a fraction, R squared over 4, I can put the 4 up there. Yeah, that makes it 8. So can I change this one? If I put times 4 here, then that becomes 8. Right. So which means, as you can see, my G is 8 GM over R squared. So usually I just do it like this. You can now look at the G, compare the G and the G nu. You see that this is G. All of that is G. So you simply replace it and you find that the acceleration due to gravity, which I call G nu on this other planet, is 8 G. Replace it with G. Right? Or alternatively, what you could do is you could write this as, we have space here, maybe something here. You could write this as G over G. Now you have to divide this under 8GM over R squared, divide by G, divided by G, which is, when your question is mathematics, you invert the fraction, so it will be times, when you divide by a fraction, you invert the times r squared over g m, right? And then your, yeah, your, you will cancel this r squared, cancel the gm, you cancel. So by when you do that, you see that you increase your g of 8. So that's how they ask them. Sometimes they can say 8g, or they can actually put the actual figures. Right, so this the answer was 8g, so if you get 8 times 9,8, the answer could be in meters per second to seconds, or meters per second squared. Okay, then the other thing that they normally like to ask here is, if you look at this equation for g, let me remove this now. Yeah, if you look, I hope you are following. If you remove this, you see that acceleration is directly proportional to the mass of the planet, and inversely proportional to the square of the distance of the radius of the Earth, of the planet. What they normally ask is prove that the acceleration due to gravity G is independent of the mass of the object. So we normally call the mass of the small m. So you can use the Newton's law of universal gravitational force equation, which says the force of attraction, which is actually gravitational force, between any two objects is big G. Let's call the other object smaller one next. This small object m times big M, all this over the distance between the particles. Near the surface of Earth is practically the radius of the Earth. So over the radius of the Earth, if the object is near the surface of the Earth. So this is the law, the formula that we derive from Newton's law of universal gravitation. Right? So Fg, the gravitational force, is actually the weight, which is mg. So we put mg. So this procedure is what you need to do when they ask you to prove that the mass, the acceleration due to gravity on the object does not depend or is independent of the mass of the object. So it does not depend. So that's why G is a constant for all objects near the surface of the Earth. So you have now your big G, small m, big M over r squared. What happens now? You see, the small m, they cancel. So G is simply the same equation that we started off with, G big M over R squared. So it only depends, it is directly proportional to the mass of the object and inversely proportional to the square of the radius of the planet, or to the square of the distance between the object and the planet. And then the other thing is, we normally know additional distance if the object is very close to the planet. We don't need, sometimes we don't need to add a few centimeters to the radius of the Earth. It's large enough to represent the distance between the object and the center of the Earth. Good. I hope you have enjoyed this. Please don't forget to subscribe to my channel, and please send us, email me if you need online lessons also. Please don't forget to get all of us. I'll be back with more videos. Thank you.